In previous tutorials we've seen examples of internal loading and finding it by method of sections or method of joints. Now I just want to look at one that is very similar to method of sections, but it's with a cantilever beam, cantilever reaction joint here against a wall, and then you have like a pipe coming out here. So the question is, it asks you to find the internal loading at the cross section shown on the diagram. So that is this line here, and so you have to find all the moments and all the forces in each direction here, which can be really useful when you get to learn different things later on in the course. So first up, we want to do a free body diagram, as with every question. So I'm just gonna, and we can take the cut literally. We can just cut it off here and pretend that this acts like a cantilever beam, because this can still support moment. So essentially, just get rid of the front bit there, if you see that. So I'll just draw that in and show you what it looks like. So now this is only 3 meters here. This is 3 meters. Oh, sorry, 0.3 meters. So we're only taking this little bit here. So that's 3 meters, and this acts as a cantilever beam, so it supports moment in the X, Y, and Z direction. So I'll just write in all the forces. 10 kilonewtons and 20 kilonewtons. Okay, so this is literally what we have now. So this is cantilever there. So we'll label our coordinates as using the right hand rule. So X, Y, Z. This is the positive axes. So now for here we want to find some of the moments in the X equals 0, some of the moments in the Y equals 0, and some of the moments in the Z equals 0. So I'll just show you, well, first we'll do the forces. So some of the forces in the X direction equals 0, some of the forces in the Y direction equals 0, some of the forces in the Z direction equals 0. So we've labelled which ones are the positive here. And just remember the right hand grip rule as well, so your thumb points in the direction of the positive axis and your fingers curl around to show that which direction is the positive moment. Okay, so from this we can go straight into doing some of the forces in the X direction. So some of the forces in the X direction, we have a negative 20, so negative 20 kilonewtons plus our Rx, which is occurring here. So I can draw them all in if you want, and then it gets a bit messy because then you have to do moments. That's mx, and then my, and then mz. So now you really can't see what's happening there, but okay. So yeah, we have this reaction force in the opposite direction here. So we can see that Rx equals 20 kilonewtons. Since that's the only one in the X direction apart from this Rx here. And so now we'll do some Fy equals 0. Again we have Ry, since we just labelled it being positive, and then minus 10 kilonewtons because that is going downwards in the opposite direction from this y-axis. So Ry equals 10 kilonewtons. Just come over here for Fz equals 0. And so what do we have? We have negative 25 kilonewtons there, and then we usually just label the Rz is positive, so plus it, equals 0, Rz equals 25 kilonewtons. Okay, so that's everything you should be reasonably used to. It's just global equilibriums, just in another dimension as well. Okay, so now we want to do the moments. So First, let's do moment in the x direction equals 0. So we can see here what's causing moment about this x direction. It's really only this one. It's really only this 10 kilonewtons force, because this is parallel to the axis, and then this one goes through the x-axis. So 10 kilonewtons is the only one, and its distance away is 0.3 meters. So we do 10 times 0.3. Well, let's see if it's going in the positive. So that's going in the positive direction, since again we use our right hand grip rule, and we see that it's curling around that way. So we get plus mx equals 0. So this is our reaction moment force. So then we get mx equals -3 kilonewton meters there. So we'll do the same sort of thing for my. So for my, we have this 10 kilonewtons force is acting parallel to the y-axis, so it doesn't cause any moment. Again, this 25 kilonewtons goes through the y-axis, so it doesn't cause any moment. But this 20 is acting 0.3 meters away from the y-axis, and so that causes moment in. So using our right-hand grip rule, in the negative direction. So we have -20 times 0.3 plus my equals 0. My equals 6 kilonewtons meters. Okay, that's right. No, that's right. So now the next one we want to do is sum of the forces in the z direction equals 0. So we're going to look at this. What is rotating about the z-axis? It's really this 10 one, since this 20 goes through it, and this this force is parallel to the z-axis. Sorry, I didn't write this distance in. This is 0.2 meters from this one above. So this 10 kilonewtons is acting 0.2 meters away from the z-axis, and that is in the negative direction if you use the right hand grip rule again. So that means we get -10 times 0.2 plus m of z. This is the reaction force, the reaction moment at that point, equals 0 mz equals 2 kilonewtons a meter. Kilonewton meters. So we've just found all of the forces and reactions at this section. So you can see that when we're doing this, we literally just cut it off there, cut it off wherever it is, and just disregard how far away it is from the wall. Yeah, and that's what you can do, which is a convenient method to do when you're trying to work out the internal loadings. Alright.